Hi guys, so today I'm going to solve an energy problem number 84 on page 168 of this textbook. The problem says the masses of the javelin, discus, and shot are 0.8 kilogram, 2 kilograms, and 7.2 kilograms respectively, and record those in the corresponding track events are about 98 meters, 74 meters, and 23 meters respectively. Neglecting air resistance, calculate the minimum initial kinetic energies that would produce these throws. So here we have the javelin, then the discus, and then lastly the shot. The problem implies that the objects are projected and continue in motion by their own inertia and the downward force of gravity. Therefore, when drawing free body diagrams for projectile problems, you should only have a single arrow pointing downward representing the force of gravity. Now that we understand that this is a projectile problem and the objects are being thrown, we have to figure out the angle that the objects are thrown. The problem leaves it up to us to know that launching the objects at 45 degrees will yield the maximum range. To solve part A, we're going to use the range equation, which is initial velocity squared times sine 2 theta over gravity, and simplified it becomes velocity squared over gravity because we're assuming that theta is 45 degrees and sine 2 theta becomes 1. So first we're going to solve for the javelin, and we know that the javelin goes over a distance of 98 meters, and we'll plug that 98 meters in as our range for the range equation. Then we cross multiply 98 meters times 9.8 meters per second squared to get our velocity squared. And that should get us 960.4 meters per second. So we want to leave it as velocity squared. We don't want to square it because kinetic energy is equal to 1/2 mv squared. So now we have to plug in what we know. 1/2 times 0.8 kilograms, which is the mass of the javelin, times 960.4 meters per second, which is our velocity squared, and that gets us 384.16 joules. Now we're going to find the kinetic energy for the discus, and to do so we're going to use the range equation again, which is velocity squared times sine 2 theta over gravity, simplified to velocity squared over gravity. Now we know that the discus went over a distance of 74 meters, and that's going to be our range. Then we cross multiply 74 meters times 9.8 meters per second squared, and that gets us 725.2 meters per second, and that's our velocity squared, which stays as velocity squared because kinetic energy is equal to 1/2 mv squared. And we plug in what we know. 1/2 times the mass, 2 kilograms, times our velocity squared, 725.2 meters per second, and that gets us 725.2 joules. Now we're going to solve for kinetic energy for the shot. And we're going to use the range equation. I'm not going to say it again. I've done so many retakes and I practically know it by heart. Velocity squared over gravity is it simplified. So the shot went over a distance of 23 meters. We plug that in for our range equation. Cross multiply 23 meters times 9.8 meters per second, and we get 225.4 meters per second, and that's our velocity squared, which we want to leave it as velocity squared because, as I said before, twice now, kinetic energy is 1/2 mv squared. Plug in what we know. 7.2 kilograms is the mass of the shot times our new velocity squared, and that gets us 811.44 joules. Part B asks us to estimate the average force exerted on each object during the throw, assuming the force acts over a distance of 2 meters. So the problem is asking us to solve for force, and we know that force is equal to work over change in position, and work is equal to change in kinetic energy, which is what we just solved for. So first we're going to find the force for the javelin, and we solved that the kinetic energy for the javelin is 384.16 joules, and the problem tells us to assume that the force acts over a distance of 2 meters. So we divide 384.16 joules by 2 and we get 192.08 newtons. Next we find the force for the discus, and we know that the kinetic energy for the discus is 725.2 joules. We divide by 2 and we should get 362.6 newtons. Last but not least, we find the force for the shot. And we know that the kinetic energy for the shot is 811.44 joules. Divide by 2 meters and we get 405.7 newtons. Part C asks us, do your results suggest that air resistance is an important factor? Yes, because the average force that the person could throw with should be the same. Well, that concludes my energy problem solving video. I hope you enjoyed watching it and that you learned from it, and thank you for watching.